Section 3.7 The Joule Thompson Experiment. First, let's look at the diagram. We have an ideal gas with an initial state of P1, V1, T1. We're about to push this gas through this porous plug. The external pressure is slightly greater than P1. Now we're looking at the final state. You have this gas with P2, V2, T2. The external pressure here is slightly lower than P2. Now let's do some derivation. 1 is the initial state on the left-hand side. 2 is the final state on the right-hand side. So how can we compute the work here? Well, let's say the P external is roughly P1. The volume change is from V1 to 0 on the left-hand side. Therefore, work is this on the left-hand side. What about the right-hand side? The right-hand side, the external pressure is very close to P2. All right, and the volume changes from 0 to V2. At the beginning, there's no gas. On the right-hand side, the volume is 0. Now, it's V2. So, work 2, W2, is this. And we integrate this to integrals. That's very easy because P1 and P2 are approximately constant. Therefore, the result is P1 V1 minus P2 V2. That's the total amount of work done to the system. And the pipe is well insulated. Therefore, Q is 0. Q1 is 0, Q2 is 0, Q is 0. In that case, we can compute the internal energy change of the ideal gas. That's U2 minus U1. The final U minus initial U. That's delta U. Delta U is equal to Q plus W. And we know Q is 0 because the system is well insulated. There's no heat transfer. Therefore, delta U is W. And W is this, P1 V1 minus P2 V2. We put them in here and we'll see U1 plus P1 V1 equals U2 plus P2 V2. U plus PV, that's the definition of enthalpy. Over here, U plus PV, that's the definition of enthalpy. Therefore, H1 is equal to H2. In this process, the enthalpy remains constant. We call this isenthalpic process. Again, the enthalpy is constant. In this process, both the pressure and temperature changes. We define this Joule Thompson coefficient mu sub j dash t to be delta t over delta p, and this is an isenthalpic process. Enthalpy is constant. So it tells us temperature changes with pressure. If this coefficient is positive and we allow this pressure to drop significantly, and then the temperature of the gas will drop significantly. So we use this phenomenon to liquefy a gas, such as nitrogen gas. Now let's look at some theoretical derivation. Given the definition of the Joule Thompson coefficient, it's delta T over delta P in an isenthalpic process. We can prove that delta H over delta P is simply negative Cp, the heat capacity, times this Joule Thompson coefficient. We will have to use the triple product rule. So first, negative Cp is negative delta H over delta T under constant pressure condition. And this is mu Jt. Mu Jt is delta T over delta P when the enthalpy is held constant. Using the triple product rule, this part is just 1 over delta P over delta H. 1 over delta P over delta H is delta H over delta P over here. And therefore, mu Jt is simply negative delta H over delta P over Cp. Remember, we mentioned this. Delta H over delta P is small for a real gas. However small it is, it's non-zero, so it's possible to liquefy a real gas as long as this one is non-zero. For an ideal gas, H depends only on T. This part is 0. Mu Jt is 0. Therefore, it's impossible to liquefy an ideal gas because it's impossible to change its temperature by reducing its pressure in this isothermic process. However, for a real gas, it's possible to lower the temperature by decreasing its pressure significantly, as long as this mu GT is positive. And it's possible to prove this mu GT, this Joule Thompson coefficient, is 1 over CPM times over here, this is 2A over RT minus B. So when this attraction dominates, we have a positive value here. The mu JT is positive. That means delta T over delta P is positive. That means if we lower the pressure, the temperature will decrease. So again, we use this phenomenon to have a real gas undergo the isentropic process to lower its temperature significantly. How significant? Significant enough to bring the temperature of this real gas to below the boiling point, and then the gas is liquefied. The proof of this equation is in supporting information.